Okay, so what we will start is showing you that even with the simple methods, you can get quite a bit of information out of your recordings, out of your data. So today I will show you in this lecture how to, with just simple cross-choreograms, what you know very well, how much you can get and achieve. So it will be showing how simplicity can be good. Okay, and this is for people who don't know Lethbridge, and from my window I can see this if I drive 2 hours west. Okay, so I'm doing mostly electrophysical recordings with rats, so I will be talking about population data analysis from tens or hundreds of neurons. So usually such data are recorded with silicon probes, which are really great to allow to record activity from this many neurons close by, so we can get good idea how the information which is coming to this cortical area, how it is locally processed. So this is cartoon, how those probes can record from neurons, and if you look at activity of one neuron, you will see that it is like ba-ba, 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 firing sometimes. But if you look at activity of tens of neurons recorded at the same time, you are getting much, much more information. Now you see that this time that neurons tries to be coordinated, that it isn't like one neuron is firing and others are silent. Rather, there is some patterns of activity, and the question is how to discover those patterns and how to discover their meaning. One of the amazing things about this slide is the following, that it is recording in auditory cortex, and here is silence, and here is presented tone. So in this cortical area devoted to process sound, even if there is complete silence, neurons are active as much as during sound presentation. And I would call it this dark matter of neuroscience, this spontaneous activity, that, you know, all the time our brains are producing some patterns, and we have no idea or little idea what is the meaning of this. So I will be telling you today about some methods how to try to decipher this neuronal code. So if you look, for example, at some code and you try to figure out what it means, well, the typical way to start is to apply some statistics. So, for example, you can look how often this wave symbol is occurring. If we would have some bigger text, then you can count how many times what is the probability of this wavy symbol occurring. And later you can take some English book and try to see what is the probability of each letter occurring. And by matching these probabilities, you can get some pretty good idea right away what letter is encoded by this wavy symbol. And similarly, we will apply the statistical methods looking at probabilities to find meaning of neuronal patterns. So in this case, I encoded sentence, "I never came upon any of my discoveries through the process of rational thinking" by Albert Einstein, so too bad to my approach. So let's see here first what we can do with the data. So when we look at this data from tens of neurons, we have this just spiking patterns, and without simplifying it in some way, it's really difficult to get idea what's going on. So the first thing what I will be showing you is how to simplify those patterns to get some, not this many different spikes, but a few numbers which are easier to work. And the first way to do it is just simply take, let's say, 100 millisecond time window and just count number of spikes for each neuron in this time window. So now we will lose information when exactly within this 100 millisecond time window each neuron fire, but we will have this simpler information, how many spikes each neuron fired. And those are called population vectors. So if we do it, we will get something like that with 2 vectors in this case with numbers, and we can do it for entire data set. And now with those just numbers, it will be easier to start analyzing our data. And the one important point with data analysis is to first look at data. So if you just apply blindly some method, you may get really misleading sometimes results. So I spent hours or weeks just looking at those patterns of activity, seeing, getting good feeling, if there is, some kind of interesting interactions that I can see by eye, and then I can apply some other methods to try to test my intuition if my eye was really catching something significant statistically. Okay, so how to look at such population vectors, how to look at this data? Well, first, let's look only at 2 neurons, at activity of 2 neurons. So let's have those vectors only with 2 numbers. So in this case, we can plot what is activity of neuron 1 here, what is activity of neuron 2 here, and for each trial we can plot dot that neuron 1, when it fires a lot, then this point it means that this neuron 2 fired very little. And here what you can see is right away that those neurons are somehow correlated, that they are not completely independent. And the other interesting thing is that it happens quite a time that when this neuron fires a lot, this other neuron fires a little, but the opposite doesn't seem to be happening. So it seems like there is some asymmetric relations between those neurons, that it is very unlikely that this neuron number 2 will fire a lot when neuron number 1 was silent. And again, just by running a simple correlation, you wouldn't get this information. Plotting this data and looking at those interactions, it will give you some better idea. Also, what you can do is look at different conditions plotted separately. So this is this populations vector for spontaneous activity without any stimulus. If I plot what was the responses of those neurons when I presented tones, those green dots are showing. For when I presented natural sounds, then it was driving more those neurons, and here. And here, but just by looking at it, you can see that, well, it seems like the population vectors in spontaneous activity seems to be quite similar to the stimulus evoke activity. That, you could imagine that when you are presenting stimulus, then neurons can be activating completely different patterns. But this doesn't seem to be the case. It seems like this spontaneous follow evoke activity. So if we have this long vectors, what to do with that? Well, we can do what is called multidimensional scaling, and this is a simple MATLAB function. So here you are giving array with all your population vectors, and here you are saying, let's reduce all this dimensionality just to 2 dimensions, and it is something equivalent, similar to PCA, that in principal component analysis, you are giving your data, and it finds what are the most interesting directions, what are the projections which are explaining the most variability. Here, this multidimensional scaling is a nonlinear method. It's just try to take this multidimensional vectors and squeeze it to 2 dimensions. And how it does is that if 2 vectors are more similar to each other, they will be closer to each other in this 2-dimensional space. So this method is looking at all pairwise distances, is looking how similar are vectors to each other, and later is putting this in this x and y coordinates. So again, this is another way to visualize your data, to get some feeling how, and if there would be completely different patterns for stimulus evoke and spontaneous, or for different stimulus conditions presentations, then what you would probably see is some separate clusters. But here, again, these black dots and color dots are overlapping, meaning that even in this high-dimensional space, the spontaneous and evoked patterns were quite similar. Now, how to quantify it in some quantify those similarities? Well, what you can do is the following, that you can, for example, shuffle order of these numbers. So now you will have some vectors which have the same overall sum, but the numbers are now shuffled, so it is order of neurons is different. So you can now compare how your activity would be similar to what you would expect by chance. And what you can do is now you can take one of those dots and see what is the closest neighbor. Is the closest neighbor of this evoke response spontaneous, or maybe this shuffle response, which are the blue one? So here, there is this function in MATLAB, distance, where you can easily do it. And what it does is just looking if this point is closer to spontaneous or to shuffle data. And by doing this, you will find that in this particular case, most of these dots, color dots, which are representing stimulus evoke responses, were much closer to spontaneous activity. So it means that, again, stimulus is not evoking completely different patterns, but rather something already existing in cortical dynamics. So here what we are talking about is population vectors, where we were binning data. And it not always could be the best solution. So if we have some spike train and the binning, it is equivalent to this, that we are looking what was the firing rate in the first time bin, in the second time bin, and so on. And here you see this kind of step-like function. So if you would start counting this a little bit earlier, then probably it would affect how those steps are distributed. That, if this border between bins would be here, then this probably wouldn't be 0, but it would be 1, and this neighboring also will be 1 bin. So better way to do it is try to smooth data. And how to smooth data? Well, so there are many different what is called kernels. So you are trying to look what is the average activity of spikes in some window. And so as you see, after the smoothing, you have this much more, which is called convolution. After this convolving, you have this much more smoother signal. So now it is less problem that as binning is causing, that if you take this bin and this, that you will have this completely different values, that now it somehow takes average in some periods. So here is a little bit more explanation what this convolution is doing. Well, if you have here spike train and you are trying to convolve with this Gaussian kernel, then what would be the value of this spike train at this point where this dashed line is showing after the convolution? Well, so what you could do is, what it will do is that if we center this Gaussian here, then we can multiply those spikes at the value of this Gaussian at these points. So basically, what it will end up is that spikes which are closer to this dashed line, they will contribute more. Spikes which are far away from this Gaussian, from the center, they will contribute less. And so if there is a lot of spikes close to the center, it will be big value. Otherwise, in this case, the point would be somewhere here after summing contribution of all those spikes. And to convolve entire spike train, you will now shift this center of this Gaussian to slightly different position and repeat this procedure. So the spikes closer to the center will have much bigger contribution. So the smoothing is really nice to somehow get some continuous signal rather than this discrete spike trains, which are easier to analyze. But now, if you have this continuous signal, you can now calculate correlation coefficients and so on. And those kernels doesn't have to be symmetric, and you can use, for example, this kind of triangular kernel to do convolution, which works exactly the same. And here, for example, it could be if you want to evaluate what was intracellular potential, for example, based on spiking activity. And other ways we can simplify spikes is, as I said, by calculating number of spikes. If this is, for example, beginning of trial, we can just disregard what other spikes are doing and only look at latency of the first spike. So in sensory systems, for example, in barrel cortex, it was shown that precise timing of the first spike, it was very informative which whisker was deflected. So looking only on the spike time of the first spike, it could be one of the ways to also simplify it. Other way is that you can smooth the signal, convolve with some Gaussian kernel, and now you can look at the position of the peak of this smooth curve, and it would give you some idea not only about first spike but also about other spikes, how they were affecting this activity. The one measure which I like to use is center of mass. So I'm calculating where to put, for example, some point that the spike train will be balanced. So I'm first smoothing it, and you have in my code, one of the functions is called latency, where if you give a spike train, it will calculate this center of mass of the spike train. So again, looking usually at single spike is not giving very reliable information. The better measure is usually look at some many spikes and find some way to combine, to reduce this information to single number, and this looking at the center of mass of your stimulus evoke response or cross-corrogram, it seems like one of the good ways to do it. Also, we can fit some curves to try to describe this spike train with some one or two numbers. Now, if we, for example, smooth our spike trains, now we can easier compare different spike trains, different activities. So let's assume that here we have smooth two spike trains, red and green, and those are evoked by different responses, different stimuli. So we want to find how similar those responses were. So what we can do is we can, for example, calculate Euclidean distance. So just subtract red curve from the green curve and calculate the absolute values of that. So looking how much distance is between those red and green curves. The other way, which is very often applied in neuroscience, is calculating correlation coefficients. So if those two signals are covariant, then it will give a larger correlation coefficient. But in this upper case, those two measures are quite consistent that small Euclidean distance is also causing a large correlation coefficient, as we would expect, but it doesn't have to be always the case. So, for example, here, this green response has a much higher amplitude. So now the distance between those two curves is much higher, so Euclidean distance would be large, showing that those spike strains are very dissimilar. But if we look at correlation coefficient, then it would be the same as here, because so correlation coefficient doesn't care about scale. So if you use correlation coefficients to look how similar are responses, you will get an answer that they are very similar. If you use just Euclidean distance or count number of spikes, then you will find that those two responses are very different. So you have to keep in mind that when reading papers, when people are saying that some responses are similar. It is important to know what type of exactly measure they use. And here is another example that, for example, if there is almost no response to green stimulus and red is also very small, then this Euclidean distance will be as similarly small as here, but the correlation coefficient will be close to 0 in this case if the red is some random signal. So again, in most cases, this Euclidean distance will give some intuitively similar results to correlation coefficients, but it doesn't have to be. And knowing what exactly measure you are using to calculate similarities between different spike trains is very important. Another measure to look at how to quantify similarity between two spike trains, it was proposed by Jonathan Victor. So here is one spike train, and here is another spike train. And what he proposed is that let's count number of steps which you have to make to get from this spike train to this. And the steps which are allowed is shifting spikes, adding spikes, or deleting spikes. So by using those three operations, how many operations you need to get from this to this? So first, we can delete this spike, then we can shift this spike, shift this spike, and so on. And after this 8 or 9 steps, we will get to this. So it is another way of measuring, and again, it could give some different results from Euclidean distance or correlation coefficient. So if you have some measure to look at similarity of neuronal responses, then later you can look at compare all the pairwise responses. So for example, here what in this matrix I'm plotting is how similar responses were of neuron, let's say 40 to neuron 1, neuron 2, neuron 3, and so on. And I'm doing this for all neuronal pairs. And here what I'm doing is I'm looking this for spontaneous activity, and as a measure of similarity I'm using correlation coefficient. And now I can do the same for example, stimulus-triggered activity. And now I can see nicely that, again, the relations between neurons are quite similar across conditions. So if two neurons likes to have a similar pattern of activity, be coactive during spontaneous activity, then they also will be coactive often during stimulus-evoke activity. And we can now calculate correlation coefficient, for example, between those matrices. So to quantify how similar this matrix is to this, we can, again, either use Euclidean distance or we can use some correlation, just correlation coefficient. So the same things what I showed you where you can use to calculate similarity between spike trains, you can also do to quantify similarity between matrices. So everybody knows what is correlation. If you have two neurons, you can look how they are covariant in time. And in MATLAB, you can use this easy cross-choreogram function where you have one and other signal. But sometimes this correlation, what correlation is, this cross-correlation is not telling you is how these relations between neurons are changing over time. So you would have to do it in different time periods. So one other method which is like an extension of typical cross-choreogram is joint peristimulus time histogram. So here what you do is plotting what was the activity of one neuron, here what was the activity of other neuron, and on single trial. So here you are concerned with two neurons. So this, it is beginning of trial. This neuron fired here, this other neuron fired here. And when there is cross-section between those lines, you are just marking this as a 1. And you are repeating this for next trial. And if again happens the same cross-sections, then it will be increased by 1, so it will be 2, and so on. So it shows you where those spikes seems to have this the same relation. So if often there would be those two neurons firing very early on the trial, then you will have a lot of points summing up here, so it would be peak. And where it could be useful, so here is an example of some paper where they apply this method to look at monkey responses in go and no-go trials. So again, this is here activity of one neuron, other neuron. So what you can see is that on average, both neurons fire with a kind of constant profile, that you don't see any trial modulation of those responses, that if you would just look simply at the amount of activity, you will find that it seems like they don't care about those trials. But plotting this joint peristimulus time histograms, it turns out that those neurons tend to co-fire, to be correlated, mostly on the beginning of those go trials. What was different for no-go trials, where monkey had to restrain itself from moving, so it has to stay still, then you see that on average responses, again, there is no difference between those two conditions, but what happens is that the same neurons tends to now correlate to fire spikes together in the second part of the trial. And if you just calculate correlation between those two neurons across this trial, you will find that these cross-chorograms are almost exactly the same for both conditions. But what happens if you look more details is that on the beginning, there is different coordinations for one type of trials for this go versus no-go trials. So this joint peristimulus time histograms is nice extension over typical cross-correlation analysis, because it allows you to look how those relations between neurons are changing over time. The drawback of this method is that you need a lot of spikes to reliably estimate those matrices. So as you know, these correlations also are used, and those are similar to spike trigger at average. So if you present some stimulus, so here, for example, is, I think, deflections of a whisker, and here is some neuron in sensory cortex, and when this neuron fire, we can take signal, what was the signal right before this neuron fire. And if we add up all those windows, what we will get is this information, what was the stimulus triggering of this neuron. So we will find that this neuron likes the most these deflections down, followed by quickly going up. So it was the stimulus which was driving the best this neuron. And this, what is called this stimulus triggered spike trigger average, is equivalent to if you would just do cross-chorogram between this signal and spike. So again, just looking at cross-chorogram can give you nice information what this neuron is most sensitive to. And it doesn't have to be one-dimensional signal. Here, for example, people presented white noise. So here is frequency, this is time. So this is sound like shh. And by looking what was this small variation in this white noise which were triggering spikes, again, they can calculate what was this receptive field, those neurons, and it seems like this neuron is mostly responding to this higher frequencies. And again, this is nothing different than just correlation, calculating correlation cross-chorogram between neuronal responses and each of those frequency of the stimulus. So why people are presenting often this white noise? Well, because white noise has this nice properties. It has all frequencies equally represented. If you would like to estimate receptive fields from, for example, some natural sounds, then, like, for example, this is bird song. Here you will find that some frequencies are overrepresented, other are underrepresented, that, birds is not singing with all the tones with the same probability. So you can still do estimate of this receptive fields of neurons in the same way, but here you have to apply some correction that if the sound was presented more time, given frequency was presented more time, then later you have to correct for that. And the other thing is that similarly as with single spike trains, we're talking that to have some manageable representation of those spike trains, we need to compress it to one or a few numbers. Similarly with receptive fields, if we have receptive fields of tens of neurons, so to look statistics, how those receptive fields are, for example, changing with learning, we can also parameterize it. So we can, for example, describe all this two-dimensional receptive field, for example, by only looking what is the position of the peak, what is the latent, at which time, and which frequency. So now all this two-dimensional structure can be reduced to two numbers. Then you can easier see if those two numbers are somehow changing if animal is learning some new song. And here is an example that just using those simple correlation can make one scientist's career. So here what I did in my work is that I look, for example, at this spontaneous activity, and on the top is multi-unit activity, which in this case is just a sum of activity of all those neurons. So if you sum up, it is what is going on, what is this multi-unit activity. And now to find some patterns, what I did is that I noticed that there is some kind of sequential order. So what I did is that I applied cross-chorograms between a single neuron and this multi-unit activity. And the idea is the following, that if some neurons tends to fire on the beginning of those bursts, then their cross-chorograms will be biased in one direction. If they are firing on the end of those bursts, then their cross-chorogram will be biased in other way. So by trying to figure out if there is really this sequential order in this spiking activity, what I was recording to, then applying this cross-chorograms between multi-unit activity and single neurons can give this idea. So we found that indeed it was some kind of consistent relation, and interestingly, similar sequences were during spontaneous and stimulus-evoked bursts. But now, when animal is fully engaged and awake, the activity looks, continuous. Now you don't see this single burst. But again, what is nice about cross-chorograms is that you can run those analyses and see again, is some, bias that some neurons try to lock to. In cross-chorograms, what you will find is cross-chorograms between this multi-unit activity and single neuron activity. You will find again, if the neurons tends to locking to the beginning of the burst or the end of the burst. And we found something similar, indicating that this is not continuous activity, but rather is composed of those sequential packets, but now they are placed so close to each other that it gives this idea of continuous activity. So basically the conclusion was that different stimuli are not evoking completely different responses, but they are rather small modifications on the same sequential frame. The other thing what we can do with cross-chorograms is that we can look how they are changing with time. So we can look, for example, when animal is exposed to some stimulus, how it will affect relations between neurons. So again, we have this here cartoon with signal recorded signal from many neurons, and we can calculate what was the relations of activity of one neuron to population activity, to sum of activity of all other neurons. And if we plot those cross-chorograms here, and they are sorted, so some neurons fire a little bit earlier than population, some firing later. and here animal was during this time stimulated every second with some tactile stimulation. If we look at activity, before that, spontaneous activity, so here was no stimulation. It was not identical, but very similar relations between neurons as we expect. But now, after this 20 minutes of activation, we see that those cross-chorograms are now much more similar in spontaneous activity following stimulation to stimulations than before. So it means that, again, using this simple method, we could look how the reorganization in this cortical networks is happening during stimulus presentation. So it means that now somehow this local cortical circuit reorganized to better represent this presented stimuli. So cross-chorograms are not always answering everything. That if the question is there that there is some random activity and only sometimes some sequences are inserted, or maybe neurons are slightly changing order of those sequences, those things are not always easy to answer just with cross-chorograms. So another way to look at some sequences and how they are changing is with template matching, that you can define some template. So look what was the pattern, for example, evoked by stimulus. And later, if you have some spikes, you can look how it matches to this template. So in this case, when looking template analysis, it's nice to smooth your spike trains, because otherwise with zeros and ones, it would be very unlikely to see any overlap with template. So you need to add some this kind of temporal jitter by this smoothing. And now what you can do is that you can take this template and look how it matches to every single part of this spike train. So we can match to this window, we can shift it and match now to this window, match to this window, and here we can plot the score, how well was this matching. So in this case, if it is exactly signal as in this template, it was very good match. Here it was sequence in opposite direction, so the match was negative. Here again, it was not exactly the same sequence, but it was quite similar. So just looking what is the overlap between template and this particular signal can tell you how often those sequences are replayed. And again, I prepared some code for you. It's not just a few lines of the code doing this template matching, so you can look, and on the end of in a few minutes I will describe a little bit this code. So you can find some ready-to-use example where on some simulated data which you can replace with your own data, you can run this template matching analysis. And we did it this, and also other people use this quite successfully. And for example, this that in hippocampus there is this replay of previous activity discovered by Matt Wilson and Bruce McNaughton. It was all thanks to this template analysis. So if you calculate some similarity between spike trains, always is the questions, well, is it this, differences or similarities can be just explained by chance? So how to test significance? Well, often what people are doing is that they are applying they are comparing spike trains to artificial spike trains. And one way to generate artificial spike train, it is by Poisson process. So here, basically, you are generating some random numbers, and later you can say, okay, whenever there was number 5, I will assign that it was spike. So here you see that with 10% probability, you will have this spike. So you will have to adjust this probability to reflect what was the firing rate of your neurons you are comparing. And with just this simple process, by generating some random numbers and saying if the number is bigger than something or smaller than something, then you will assign spikes. You can generate this Poisson spike train. And again, so here is one line of code in MATLAB where it's generating this. So here what you see is that this comment is generating just 100 random numbers between 0 and 1. And if those numbers are smaller than 1, then MATLAB will interpret it as a true, and it will mark it with 1. So with this simple line of code, you will get 100 numbers, which will be zeros and ones, with 10% of probability that you will see this spike at any given position. Because we know that spike trains are not these randomly generated processes, often when people try to estimate if there is some changes in neuronal activity, they do usually shuffling. And they can do different type of shuffling. So here is the simplest, where just, if you have 10 neurons, for each neuron, you can shuffle trials. So for this neuron, when it fires patterns on the first trial, you are shifting this, that now it will be on trial 2, and so on. So now you have data where all the neurons have the same overall firing profiles, they have the same firing rates, but what you are destroying here is relations between neurons. So if two neurons were, for example, monosynaptically connected and they were very likely to fire together, after the shuffling, their correlation should decrease because each neuron will be trial shuffled independently. So this gives you idea if there is really some interactions between neurons which are going beyond what is just triggered by stimulus. Another way to shuffle data is to move spikes around, so you can bin your data in some intervals and now, for example, not shift the trials, but shift those spikes within trials. So here, for example, this red spike was shifted here, the blue spike was shifted up, and so on. So what it gives you is, again, overall, each neuron has exactly the same number of spikes at each trial. If you look at the sum of activity of those neurons before and after shuffling, it would be, again, the same profile. What will be different is that, again, all the interactions between neurons which were not explained just by stimulus will be destroyed. And you can look, is this correlations between neurons somehow indicative that those neurons are functionally connected or not? And the other way, which is also quite popular, but I think is a little bit less powerful, is just jittering spike time. So here you are just adding some short, small jitter to the spike trains, and now you see how much you can compare, how much exact, precise timing is important for interactions between neurons. And you can compare it to this shuffle data, and it will give you idea, is this precise spike timing important in this case or not? Okay, so as you got in emails, you got all the code for my lecture here, and maybe later you will have in all the code from all presentations somewhere in the Dropbox. So there you will find code where I used to generate some artificial data. So here you have data with some embedded sequences. Here is just shuffled random spikes. And now what I did is first, here is the code which just a few lines which are generating these sequences. So so here, first to demonstrate cross correlations and how to calculate latency between neurons and how to calculate templates, I need to first generate data which has some sequences. So this is the...
Which file is this? This is export or...
Yes, so this is this... sorry about that. Yeah, I think it was this Xcore example code. The longest code, it is this one. That's a good point. Sorry, I forgot to put the file name. So basically what I'm trying to do is I'm again using this random number generator to assign some times, and later with some probability other spikes are locked to this first neuron. So later I can look at cross-corograms between for the data with sequences, for the shuffle data. I can calculate what is the latency of those cross-corograms, so it will measure what is the skewness, and it tells me if this neuron is locking to the beginning or to the end of this population activity. And on the end, I can look how it can discover the sequences which I already put some specific order of neurons, and later by those analysis, I'm showing that I can recover the same order of sequences. Next, I'm demonstrating the same, that those sequences can be discovered with template matching. When I create some template to discover those sequences, I'm presenting also this few lines of the code, how to match this template to this data. And this is one of the figures which you should get when running this code. So unfortunately, I'm running out of time, but if you run this code, it is not more than few lines for each of those procedures. So this code I did my best to describe in a meaningful way. So you can, if you have some problems with following what exactly this is doing, feel free to contact me. But with somebody with minimal MATLAB experience, this code should be enough to show you how it is done easily on some artificial data, and you can apply it to your data. Okay, so it's for me, and the next speaker, it will be... Any questions?
So do you have any question for Artur?
No questions.